Good afternoon. Hello there again. This is Desmond Aubrey of Rarefied Technologies Southeast Asia, or RareTech for short. And I'm continuing with part 4 of the presentation on modular shell-and-tube heat exchangers. Just a note to say, if you're hearing a bit of background noise, I'm trying my best. I'm in a very hot environment and I've got the aircons on. And it might have a bit of noise. I've tried to depress the noise, but if it's a problem, just turn your volume down a bit. It should be okay. You can hear it. I'll try to tweak things a little bit better later on. All right, thanks for your patience. All right, so let's just pick up where we left off last time. We spoke about U5 applications. That's the larger of the exchanges in gold mining. And what I mentioned earlier on was, for instance, we were faced with this particular project, and what it was is the clients were looking for an economizer, potentially to recover energy, a heater, and possibly a cooler. So what an economizer does, it takes hot return and fluid and puts it through the exchanger and counterflow to an incoming cold stream. So what you're doing is you're starting to recover energy. It actually saves you having to put in more heat, for instance. It saves you on the heating bill. So the way the elution process works, it comes in as eluent. It's called eluent, typically around 25 degrees C. But it's got to hit the elution column at 135 degrees C. That's the specification. During the process and in the column, it starts to lose a bit of heat and it gets down to about 130 degrees C. Comes back at 130, no matter how hot you've got it, right? Comes back at 130 and it comes into this thing called the economizer, and then you let it go out at 65. So you're letting it go out at 65, and you can actually use this beast here to do a lot of energy recovery for you. If you didn't have it, you would actually have to literally put in all the heat you required from 25 to 135 and take out everything from 130 to 65 to control it. So in other words, what you put in, you've got to get out. There's a little bit of loss through the column over here. And it can be quite expensive. You know, the cost of heating, it's not cheap. You know, generating steam is pretty nice. Certainly in South Africa, they would work on probably typically about 6 bar steam, wet steam. And then you would condense that down and pass it out as condensate, which you could recover, and then you could push it back to the boilers again, as long as it's clean. Okay. And then the through steam traps and so on. The other way is to use hot oil, and then they would use, what they did in South Africa is they would use a hot oil generator. It would pass around a coil that's located in a vessel, and then you would blast a burner down into the center, and they would actually heat up the oil. But it's expensive oil. It's very expensive. You've got to use special oil, otherwise it carbonizes. And hot oil's quite nasty in terms of, I've had a lot of work with hot oil in the past with bitumen heaters that I've developed. But you've got to really know what you're doing. Okay, so steam is a lot safer for most people, a lot less dangerous. You're not using superheated steam. So the brief from the consultants who were working on this process, it was new at the time, and it was certainly new to South Africa. And they were recovering from the gold mine dumps, essentially the tails that had been put into gold dumps. And then they thought, hey, let's recover this, and we can get some gold out of it. So the idea is to put it through this process, which, to the best of my knowledge, it was developed in South Africa. So the idea is, okay, we have an economizer, we've got a heater, and we've got a cooler. What sizes should they be to minimize capital cost? At that stage, the discussion wasn't really to do with utility cost, which is something that most people don't realize. Just to throw in a bit free here, when you have a water cooled, let's say if there was a water cooler here, the cost of the cooling water, if you look it up internationally, and the South African prices and the American prices and Saudi prices and so on, it's actually very expensive. And most people don't realize it. The cost of cooling water is quite exorbitant. And not only are you saving capital if you don't have a cooling, trim cooler as they used to call it, but you're also saving a lot of ongoing costs. And I did a study, and I'll discuss that sometime, about that, and showing, in fact, that huge investment reduction and utility reduction by knocking out this trim cooler. So what I did is I actually took the inlet as fixed. I then said, okay, let's make the first one 30 degree out. And then that becomes 30 degree into the heater, 135 out. And then I come back at 130. And then the trouble is, at this point, I would then be only getting 5 degree out of it. So I'm coming back at 125. Then I've got to put a cooler. So I stepped through the design, stepped it in steps. And the next one was 25 to 35. And I walked through, right through the whole study, designing along the way and putting prices to everything. And then eventually got to a point which said, you know what, the optimum point is actually when I have no cooler at all, and these are the temperatures in the system. 130 in here, 65 out, 25 to 90. Now remember, they'll match, you know, because if you look at the heat balance, and I'll talk about heat balance in another presentation, explain what we're talking about, but because they're the same fluids fundamentally, they call it coming in as eluent and going out eluate, but there's a little bit of trickery going on in here and conversion, but it's essentially the same stuff. So you would expect temperature drops to be the same, because it's the same flow rate that's coming through here. But we'll discuss that later. So this then eventually, we were designing these sets and sending it up to the gold mines, and it really did very well. As you saw in, I think it was part 1, that I was going through the way we looked at, you know, the profitability on the mines, and they were prepared to pay a good price too. And they were pretty reasonable materials. You know, we didn't have to go stainless through the whole thing, stainless steel tubes. The rest was mild steel. It was adequate for this application. We didn't have to, I don't think we had to go through stainless on all of those. I stand to be corrected, but I don't think they were all stainless. Mild steel sufficed in most cases, to the best of my recollection. Alright, so then we go from there. Let's have a look and see if it decides to advance. Be nice. Doesn't want to. There we go. So, this is what some of the units look like. Whoops, I've gone too far. It has a jerk to this thing, so this is what the units look like. So a typical, let's say a gold mine, what you'd have is the economizer, which is what I showed you before, is going to be the bigger of the two. And then you've got a matching heater. Now, what I find really odd about some of these designs here is that the flow rate through the economizer and the flow rate through the heater should be the same. So sometimes you can get it, let's say 4 over here and 3 over here, for instance. But these are ones probably designed after my time, because I would have probably been quite careful here about this. I might have reduced that to a 3, for instance. But it depends on my flow rates. But this one to me should be probably 3 by 1 or 3 by 2, but being a little bit, because you're handling the same flows. If you go back to this picture, it's the same flow going through here, the same flow, the same mass flow. The volume will change slightly, but not that much. Okay, so sometimes the matching, you've got to be a little bit careful on that. Sometimes though, we had to pull a few tricks because of pricing, and had to be a little bit careful on pricing. Okay, so this would typically be heating, and this would be the economizer. What we're seeing here is a big one. This is a big unit, very long. You can see that's really recovering a lot of energy. So it was originally designed as a 4 bank, or 4 in parallel, and then 1, 2, 3, 4, 5, 6 in series. So very long unit. So this would have recovered a tremendous amount of energy. And then what's happened over time, they decided, all right, we don't want that bank, let's take it out, for whatever reason. Sometimes their process changed. And this again was made of, probably, I came back and saw this years later. And then what I did is, when I took over the project, I started to get the stands sorted out properly. For instance, we put side support. So I not only supported it vertically, I supported it laterally. And I put supports in between the modules as well. Whereas this is their original kind of system, which is very ropey. I wouldn't even want to lift a heat exchanger with these lifts. To me, it's a bit dicey. I think the whole thing will slip off. Whereas with these, it was actually balanced, and in the actual positioning, I set it up so that because your headers are heavy, you know, at the ends you've got manifolds, and there's turnaround headers here, but this is the heavy end. So I had to set my position points to manage this properly, so that my piping wasn't under too much stress. You don't want to dent your shells or anything like that. So it was a very tough stand, but this was an economizer. an elution economizer. So you had CRP version and CLR elution systems for the gold mines, but they were very profitable, and I think some of their chaps tried to maintain them, but I think they found it a little bit more of a meal. You need a person who knows these very well, and the builders we used to have were very good. They would just get on with this and straighten them up and do a good job with it, and pull out the bundles and clean everything up and then put it all back together again. And we had repair contracts with the mines to do the repairs for them. One of the things that I should just mention while we're talking here about the gold mining process, I discovered this years later, was that there's a certain amount of uranium that always is present when you've got gold ore. There's always a certain amount of uranium. So these units actually used to have a certain amount of radioactivity, and the mines used to have to try and deactivate them. But I don't think, in later years, I don't think they did them properly. And the manufacturers, I was quite worried when I took over the company. I wanted to cross-check the radioactive levels and so on, so that our labor didn't get under under difficult circumstances, But I think a lot of people don't realize it. And I think some of the South Africans that are still, there's only one company left trying to make, but they will never be able to make big units like this. They don't have the know. But it's really, you've got to know what you're doing. You've got to be careful. So go to the next one. Let's talk now about sugar and the sugar industry. And this, from recollection, this is where Gasalta, the original developer, this is where he got into, made his units. In other words, sugar processing, sugar juice coolers, mash feed heaters, works nicely. Sugar-based processing, furfurols, a lot of furfurol units for the sugar industry in South Africa, coolers and economizers, rum coolers, they make a lot of rum from the sugar cane. Acid heaters and coolers, solution coolers, after coolers, preheaters. So this was very popular because you could add an extra module to recover more energy. You could put another bank in parallel, split it up, do what you like. It was Meccano said. Supporting operations for the sugar, things like oil coolers, of course, turbine oil coolers. I explained that in one of my other presentations, where what you're doing is you've got oil that's circulating in the turbines, and the turbines are steam turbines, and they're used in the for some of their big instead of electric motors, they're using steam, and you've really got to control the oil properly. If you don't get it right, you damage a turbine, and turbines are very expensive to replace. So they obviously make steam. What they do is they make steam from the waste, the gas and so on, from the sugar, and then they then make steam and they can then push it through the turbine. So it's cheap, it saves them money, it's energy recovery. Things like gearbox oil coolers, all your big gearboxes are going to have an oil cooler. You pass water through the oil cooler and keep the gearbox, especially the big ones, the sugar industry and so on, keep them cool. Vacuum pump seal coolers, demineralized waters, heaters and coolers. Demin is quite tricky stuff sometimes. Effluent coolers, plenty of that. Steam and energy recovery, steam condensers, feed water heaters, condensate coolers, and steam instant calorifier. They call it instant calorifier. You've got steam, you've got water coming through on the tube side, and on the shell side you will actually condense steam, and it'll instantaneously heat your water. You don't have to put it into a tank and then slowly, progressively wind it up. It heats it instantaneously for you. And then if you go into the next one, oil coolers, again, a whole range of these, and some of these got really big. Vegetable oil, so cooler heater economizers. Sunflower oil, the same thing. Oil economizer, Dowtherm heaters, bleached oil, fish oil, fatty acid, tallow, marine oil, slop oil, air pure oil, decant oil, gearbox oil, engine oil, bearing oil, you name it, turbine oil, dredger oils for the dredgers that dredge up the sand of the ocean, crusher oil, compressor oil, thermal oil, waxy oil, different types, transformer oil, quench oil. Quench oil is where you're trying to quench components. They use these in the railways in South Africa. So you've got oil and you're trying to keep it cool, and then so you're quenching parts to harden them. And the oil get pretty hot, so you're going to take the heat out. Hydraulic oil, soluble oils, fat coolers, and so on. And the thing is to remember, when you're working with oil, as I mentioned in one of the other videos, it tends to give you a laminar flow, which is very poor heat transfer. And then the units can be massive. So what we do is we put the oil on the shell side, outside of the tubes, And then we use mechanical turbulation. In other words, because of the spiral baffles, you're actually generating circular flow, and you're actually mixing things up a little bit nicely, but in a nice way, and you end up with a pretty good heat transfer coefficient. So these units turn out to be pretty good. That's why we put the oil on the shell side. All right. And then moving on to some of these applications, you start to get larger. If I remember rightly, I think this was a phosphoric acid system. And it was, if you look at the stand, obviously the flows were in and out. Or this was just blanked at the end to clean, I think, later. So you would come in. And then these end caps, I would have actually put them down, actually, normally. But the guy, he's like that. And so you can drain the thing. But he probably didn't bother when he built it. I would have had them down so I can drain out of the thing you got them. And this is a schematic of it before building. And then the builder gets this and he goes ahead and he builds it. All right. So you get it, you draw up the ISO, and then you end up. Sometimes we didn't do. We just did a normal I think A3 drawings. Some are a bit bigger. Depends on what we were doing. And then you go along. This is now this particular unit which I spoke about earlier, and that's the ISO of it as well. We've got a bit fancier sometimes, but I really, in this one, I have to say I don't like the supports. I feel these are too flimsy. You've only got vertical support, but there's nothing on the side, and if you have a problem lifting, this whole lot's going to come loose. So I put a lot of work into cleaning that all up, doing a better job of that. All right, and then you get to this one is actually quite interesting. This was built, funnily enough, just before I got back to this company that I eventually bought. They had done this project, and it was to replace a plate heat exchanger of all things, in a very tricky application. And you'll find these materials here are Synicro, really expensive stuff. Synicro is really not cheap. And the original design, for some reason, the previous designer had done a mild steel and Synicro combination. So for the aggressive fluid, he'd gone for Synicro because of price. Obviously, he's trying to bring the cost down. And so this whole construction, I mean, you see, it's a 48 module unit. Quite a task undertaking, And in this case, you've got, if I remember rightly, 12 in parallel, 4 in series, which you see going in series. So you'd come in and then go down, and wrap, come back. This was a monster. I think it was a company called Scorpion that it was for. And the guy who was commissioning it, what he told me, is that when they started up, they'd had a few little leaks, which you normally just nip up, with the torque wrench, and you nip it up and it's fine, stops. If you get any online leaks, pick it up. Because normally it's pressure tested and everything else, but during transport, things can come a little bit loose. And so they should actually go through, before they commission, they should re-torque everything and just double check everything's to the right torque, But what happened is there were some leakages, and it actually got onto the mild steel parts, and it completely they just fell apart in front of his eyes. He was like, what now? And so they had to literally bring the unit back and completely rebuild the whole thing in Synicro, all the parts. I mean, to me, when you design a unit, you shouldn't try to penny pinch, because it's going to go wrong somewhere. And it was really aggressive stuff that they had, and it just chewed up the mild steel parts. They collapsed. So they had to go and redo the whole thing in Synicro, and I think it cost them a little bit of money by perhaps whoever designing wasn't thinking clearly at the time. And people can make mistakes. Normally the client should be checking, but the client probably didn't think. They probably thought, well, I've got a plate exchanger and it's all Synicro, it must be expensive. So, I'll replace it with something else, but I think it cost our company a bit of money. As I say, just before my time. And then you go on to conceptually mega, but I mean, practically no one's probably going to build like this. But you can put them in banks, and you can then just put them together, place them together if you want to. But you can get to the ends, you can pop the ends out, you can do everything in situ. You don't actually have to take the whole exchanger away. You just unstrip it and work on it while it's there, pull out the bundle, put another one in. It's very easy. It saves you having to lift heavy things around, So it does save you a little bit of. But again, I think that's a little bit over the top. I'm not sure if it was ever built that big. Might just be conceptual. And then this one, I'll end with this one today, because I think this one tells it all. This was up at a gold mine, And if I remember right, this was an electrolyte cooler. And the original one was this big fellow here. Look at the size of it. And what I can bet happened is that there was a mismatch in flows on the tube side and the shell side. And then one dominated, and you ended up with this massive beast. The modular equivalent is this little thing here, and it does the same job. In fact, so much so that the guy who was in charge of that project, he was an independent contractor, and he'd sold this thing onto the mine. He went through quite a few over time. He put more and more in different projects and did quite well out of it. I had feedback from him later. In fact, when I showed the picture once, he said, "Hey, that's my truck." So, yeah, that's the reality. And the main reason, really, because in the flows like this, you end up with a lot of flow in series. You might have two passes, but a lot of the flows are in series. So you end up with a lot of thermal length. Okay. Actually, out of interest, if you're trying to do plate exchanges, you've got to get thermal length depending on the amount of heat recovery that you're looking for. And plates can get quite big too if you're not careful. But this is where these units really do well. They handle these nice thermal lengths, and you can recover energy very well. And again, it actually turns out a lot cheaper, this unit, than that unit. I mean, this is frightening. Look at the size of the flanges and the thickness and the schedule for the flanges, and the end caps must be huge. And if you've got a problem with a tube, what are you going to do? You know? So most of the time they block off tubes, and when you block off tubes, it makes it worse. So I call this thing Braveheart, you know, this little fella that could take on such a big guy and beat it, actually. And obviously at a lot less cost as well. And this, of course, is a good success story on the product. You know. Again, small stand, but that's probably okay for this unit because it's not too big and it's not too heavy. It's only 4 modules. So what I'll do, let's have a look. Yeah, next one I'll talk just quickly about the technology on offer, and you know, at this stage of the game, I've got all the technology here. I've actually updated the software a little bit too to make it a bit more user friendly, but it's available for sale for various options, and we can talk about that in the next presentation. All right, I'm going to stop it at that point. Yeah, and stop it at this point, and just thanks very much for listening. So after this, we'll go into part 5. It's got quite long.